So yeah, I'm here today to talk to you about Wolfi. We're calling it a secure by default distro for curing container CVE chaos. It's a bit of a mouthful. It's not specifically for that, but one of the things that Wolfi does through its architecture is to help with CVEs, and it's pretty relevant to the audience here. So here we go. First, me, I'm Jamon. I'm on InfoSec Exchange. I live near Niagara Falls in Canada. I like riding bikes. I like working on watches. If you're at all interested in watches, come talk to me later. I'd love to go check out some shops in Austin. I also teach a course called Introduction to System Administration at York University in Toronto. And I think I was doing the numbers before this, and I'm almost at 900 students over the last 6 years. And that I just do outside of work at ChainGuard. I like to sort of help out. I want people to learn some of the things that I wish I had learned up front, early on in my career. We're here to learn about Wolfi. So first off, a little bit of setup if you want to do the demo sort of lab part at the end. I don't know if the network is going to be conducive to it, but you can watch me do it as well. Tiny bit of setup if you want to follow along. We're going to talk about a little bit of the state of the art, or just the state of software supply chain security itself. Talk about how containers are typically built today, some of the different ways of building containers. There's sort of the Docker way, there's the distroless way. We'll talk about how we build containers with Wolfi as well. And then at the end, I'll actually show you, Wolfi. I'll show you what packages look like. We'll show you how you build a package for Wolfi. How do you take that package, build it into a container image, and get all the benefits of all of the things we're going to talk about. So if you want to follow along, I would suggest cloning this now, just again, because the network might be a little slow. So GitHub, Jamonation, hello-Wolfi. You can grab that. This will be up after the conference too, so when the slides are up, you can just follow along, take your time, work through things. So setup steps, prerequisites. You've got to have Docker, some way of running Docker, whether it's Docker desktop, Rancher desktop, a server that's running Docker, Windows subsystem for Linux, however you want to run Docker. To be able to do this, just to get up to speed with sort of the current state of things, you're going to want to have Docker. For doing scans, for looking for CVEs, you want to have a copy of Gripe. Now, if you install Docker and you use the SDK image that we use for building Wolfi, we include Gripe right in that. So you can just use Docker and you can use the SDK with a built-in Gripe. It's database updates, you can scan images, and all of that. If you want to run things locally, then install a local copy of Gripe. You can also use Trivy or any of the other scanners that are out there. For us, we're going to use Gripe.
Any particular version of Docker you recommend?
Whatever works, essentially. Yeah. As long as it can build an OCI compliant image, you're all set. And that's the goal with all of these tools that I'm going to talk about. Everything at the end of the day now is an OCI image. It's a specific format. It will run in any OCI compliant runtime environment. So anytime you've got a run C, these images should just work. So current software supply chain security, state of the art, also known as spooky time. Once you start to look under the covers, once you start to poke around and start to look at images and how they're built and where they come from, it gets pretty scary pretty quickly. You might question whether you should be using containers at all if you start to really dig in. I think we've probably all seen this, versions of it. We even have this at work. We've got a joke. We got one of our staff maintainers, and we just put a picture of him right here because he's maintaining this chunk of the company, right? I think we're all familiar with software that's built with this one little tiny piece that's holding everything together. And in container ecosystems, it could be that simple. It could be something like OpenSSL, or recently there was a zlib vulnerability that came out. It could be a glibc. It can be almost anything that is that critical piece of the ecosystem that you're relying on, maybe without even realizing it, right? You pull in a dependency, you go ahead, you build your software, and what do you know? You've shipped a critical CVE into production. That's kind of what this diagram is meant to represent. This came out from last year from OpenSSF. They got a bunch of stakeholders, different institutions, individuals. They sort of surveyed everybody, looked at their software stacks, and came up with this number that about 70 to 90% of any stack that's been deployed into production, 70 to 90% of that consists of open source software. That's not to speak ill of open source software, and I've spent 20 years of my career working in open source. I believe in open source. It's fundamental to everything that we do on the internet. But it's something to take note of. And you start to think about it, and you start to look at something like this, the visual metaphor for this is all that open source software. This is all that stuff that you're pulling in. When you do npm install, or gem or Maven, or whatever tool it is that you're using for your application and your ecosystem, you're pulling in all these unknowns. You don't really pay too much attention to them. I think in this group, probably we do. That's what the business of software security is. But a lot of people don't, right? You just go find the latest and greatest project on GitHub. It's got 10,000 stars. It's sponsored by somebody, and you pull it in and you use it. It's okay. That got us to where we are. There's nothing wrong with that approach. It's again, one of those sort of implicit assumptions that all those things that you're pulling in, they're all looked after. It's externalizing that risk and thinking, well, somebody else with this 10,000 stars on GitHub they're looking after my best interests by making sure their product is secure. And do you really know that? Can you take that for granted? I don't think so. So another stat, when you start to think about a software stack and you think about some of the risks, this was from IBM 2 years ago. This was the average cost of a data breach. Now, I don't know what their selection criteria were. I think they're talking about sort of specific Fortune 500 type companies. Globally around the world, they averaged it, and I think that it was like 4.5 million. And this is, encompassing all sorts of different countries. Healthcare, they called out specifically because it was like 10 or 11 million dollars. So the risks are higher there in that domain as well. And so why are we talking about this? Well, the risks of breach, we start all the way at the beginning. I don't know, shift left or right or whatever you want to call it, but the software supply chain itself there are vulnerabilities. Every single point of how software is built, distributed, run, there are certain threats. So you can look at things like these. I mean, every week there's a headline like this. Remember Log4j? Everybody likes to talk about that one. But recently, there's been lots of people doing research about, say, typo squatting, uploading malicious packages to PyPI, WordPress plugins. I mean, it's endless, the number of different ways that you can get somebody to run malicious software. I guess the big one as well, the SolarWinds. That's the one that kind of created the executive order around SBOMs. That really got everybody's attention because that was deep in the supply chain. That was, large institutions all across the world, the United States, using that software that was deliberately Trojaned. Nobody really could even attribute it and figure out what was the point of that attack. And it was just there. So these things happen all the time. You can call it security, insecurity. I don't know, it's great that we find them. It's great that they go from O days to actual, okay, there's a CVE that's been assigned, there's a patch that's out. We can all go and we can do some remediation and we can fix these things. It's great that we know about them, but the problem is they're still out there, right? So a little more relevant to OWASP, looking at some numbers. Again, this is on 2021 top 10. And the top 10, number 6, was vulnerable and outdated components of your software stack. So the community voted at number 2, which is really interesting. I don't know, again, what the methodology was. I don't know how OWASP collected the data about what makes it top 6. I think they surveyed 30,000 or so packages and enumerated what are the CVEs there, but I could be wrong there. So one of the things you can do to fix that, I think, to mitigate it, is to go, let's say you're using containers. I think we're all familiar. You do your apt update, you do your DNF update, you go remove all the archive files to make your image a little bit smaller, and you feel good, pat yourself on the back, and you move on, right? Thing is, we had an intern this summer do this. I went and looked at the top 10 images on Docker Hub and ran apt update and DNF update, and what happened? On average, reduced CVEs in those images by about 5.5%. And you might think, okay, well, it's still a reduction, but some of those images had 700 CVEs in them. So a 5% reduction of 700 is statistically, it's irrelevant. You're still shipping a massive amount of vulnerable code in your container. It's a best practice. I don't think you'll find any well-respected image that doesn't do that apt update and so on and so forth. But is it really even effective at that scale of number of vulnerabilities? This is just a chart showing that same work, if you're curious. So we looked at popular language ecosystems: Python, Node, PHP, Memcached, Redis. Of course, we're comparing them to our images that we're building, that they're starting off with one maybe 0 CVEs, and the number doesn't get any bigger, right? So not to sort of toot our own horn, but just to show that it can be done, to show that you can still build application components for your software stack using familiar Redis, memcached, whatever language system, ecosystem you're using, and you can ship to production with 0 CVEs and still have that same runtime environment that you would expect from a normal popular Docker Hub image. Here's just another set of comparisons. This was looking, I think it's 2 days out of date now, but looking at Golang. So if you're using Go, you're pulling Golang, you're building your images using that. There's a couple of criticals. You can see them right here. This is this little sliver. But that number, I mean, even though it's gone down from, say, 130 to 90, there's still a lot of CVEs that are right there in your build time environment. That's a supply chain. That's a point of vulnerability, right? That's your building code. If you can pull off like the Ken Thompson reflections on trust, where you can backdoor your compiler to insert backdoor versions of your compiler in itself, that's the kind of attack that can be pulled off in a build image like that.
Have you filtered out like exploitable versus non-exploitable?
This is a good question. You can look at those links below, and there's a disclaimer. So this is just a copy of the gripe scan on that image, and that's including low, unknown, those types of. It doesn't say what's the difficulty. Is there a proof of concept or anything out there? It's just a raw number of CVEs. And in a lot of organizations, that's the big thing, right? You've got somebody who's in your compliance office, and they're saying, sorry, there's 500 CVEs. I don't care if they're negligible, if they won't fix, if the vendor has said, these are not exploitable. Somebody's going to say, too many CVEs, we're not going to let you ship that to production, right? So that's kind of the thing to be thinking about. Another one over here, Python. These graphs aren't adjusted. It'd be nice, but this is 3 times as many. This is a Python 3.12 image. So the latest and greatest Python image, it's got 300 CVEs generally at any given time. So that's kind of a shaky foundation to be starting with, building your application and wanting to ship that to production. So let's talk about building containers. How do we actually get our code and make a container? Some people we might be familiar, but just for a quick refresher, we'll show you how it works. So this is a great example. Let's say you've got a Go program, main.go. It's just printing hello world or hello Lascon or something like that. And so we're pulling in the latest Golang, Go 1.2.1. It's got all the latest fixes and everything in it. This is a great Docker file. I really like that one. Sorry, it's getting texted here. This is, you can read this if you're familiar with Docker, and you can kind of reason about it. You can get a pretty good idea of what the final image is going to look like at the end of the day. So there's a worker, you're copying your code in, you're compiling it, cgo enabled 0, that means you're statically linking it, which is great. You're reducing a whole bunch of different types of attacks about library preloading, things like that. Then you're using the scratch image, which is just basically the smallest image I think you can get off Docker. There might be a couple other smaller ones. It's just enough with like a glibc runtime to be able to load an ELF executable. That's really all that image can do. You're copying in some CA certificates as well. Maybe your application, for some reason, it's doing some TLS stuff, so you want to have some certificates in your trust store. And then you're copying your built binary into your final image, setting your entry point. This is a great image. I love this. There's nothing wrong with this at all. So again, that's the thing to call out right here, the cgo enabled bit. But I put it to you that this is like that piece of art that was at Art Basel in 2019, where someone taped a banana to a wall with some duct tape, and he sold copies of this for $120,000. He sold 3 of these. It came with a certificate of authenticity. It was a legitimate piece of art. And I put it to you that our approach of building a binary inside of a container and then shipping it into production, by saying that it's a container, it's like saying this is art. Is it art or is it not? What have you really accomplished by containerizing this application? Is it reproducible or is it not? This was an actual banana, so there was no instructions when these people bought this piece. What do you do when the banana rots, right? There's no sort of follow-up or anything like that. This is not, I think, a sustainable, reproducible, automated way of building secured by default containers. So what are some of the alternatives? What other options do we have? So this is a good one. If you're familiar with the Cloud Native CNCF, Cloud Native Computing Foundation, If you're building Go applications, KO is a really great tool. KO lets you build your Go applications, push directly to a registry. It does that same thing. It strips out all of the other different components that you'd find in an image, like a package manager, any kind of platform tools for, say, interfacing with like a kernel or anything like that. And it literally is just enough to be able to run your application as a static binary for the most part. You can use KO with lots of different base images as well. So if you have a specific environment, a specific Go image that you want to use as your build environment, you can do that. Terrific. Other systems, other tools, Jib. If you're in the Java ecosystem, Jib is out there. I think it's like 20,000 GitHub stars. It's incredible. Jib is great because it lets you, instead of recompiling your whole application, let's say it takes 30, 40 minutes to build your application, you can rebuild a dependency as a layer, and so you just have to rebuild that layer. And then Jib will reassemble all your different container layers into the final OCI image. So it cuts down on your compile times, and you still get a reproducible build, a reproducible image at the end of everything. Another one, Bazel. Bazel came out of Google. I think they use it internally. It's got a different code name. Bazel, it's huge. It's got it. You can build basically anything with it. It's a big make tool, kind of built around macros. Don't quote me on that. I've shied away from ever learning it. Not to speak ill of it at all. It does amazing things. Same thing. You can pick your package. You can build your package in a sort of a secure, hermetically built environment, and you can turn that package into an image. And so you can build container images that eliminate all these different supply chain attacks by using a tool like Bazel. Also distroless. So sort of starting to get away from Docker build, that Docker file that has all those different dependencies. Bazel, KO, Jib are kind of doing this thing that's called distroless. There's sort of, well, how do you want to define it? This is the definition from Google, sort of have been championing this or pioneering this. So distroless images contain only your application and its runtime dependencies. They do not contain package managers, shells, or any other programs you would expect to find in a standard Linux distribution. So that's the really important part. There is no apt update. There's no bash. All those different things that, if you're an attacker, you're trying to get in, there's probably not going to be a set UID binary that you can run to elevate privileges with. It's really just enough to be able to run an application. That's the idea with distroless. So this is, say, what non-distroless containers look like. I maintain this list of just some comparison images that you can look at. This was just one CVE that popped up. Look at all these images. We're talking about things like Elixir, Clojure, Erlang, Golang, Gradle. The list just goes on and on. This is a really big one. These are packages that are including OpenSSH. Why is OpenSSH included in that container image? Is somebody doing something with their GCC compiler that they need to have OpenSSH included? I hope not. Otherwise, I'd like to meet them. Maybe you're doing some really interesting research and there's something there. But for the most part, you don't have to have these things in your containers. And that's why distroless has come around, because you can just, again, eliminate all of these types of vulnerabilities. You don't have to worry about SSH being in your container if your application isn't doing anything to do with OpenSSH. So this is the same thing. You don't need your Linux distribution in a container. There's really no point. You just need what's required to run your stuff. So an executable loader, whatever dependencies your application has, and you're all set. That's what a container should do. That's the sort of idealized form. But even distroless has some problems. So here's a gripe scan against the Node 20, the latest LTS. I think it was just LTS recently. And so far, so good. We're looking here. This list is a lot smaller than if you were to look at the regular Docker Hub node image. But, it was so promising. And then we get to the bottom, node. And look, it's a binary. So you can't do apt update because you don't have any package tools. And we're shipping with a high CVE vulnerability right here, 44487. I don't know what that one is. I haven't looked into it. That's the latest and greatest, and that's using distroless. So again, if you look at the actual node image, I think there's 700 vulnerabilities or 300. We've got an order or two magnitude reduction in CVEs. That's great. I would not say to you, don't use distroless if this is going to get you a step closer to reducing the vulnerabilities in your deployed software, absolutely. Go to distroless. If you can get your application to run in a distroless container, I think there's Python, Java, Node. They cover sort of the big 6 or 7 open language ecosystems. But we can still do better, right? We saw that you can ship 0 CVE containers that can run your applications in Python and Ruby and Java containers. So that brings me to Wolfi. That's why we're here today. So Wolfi is kind of an OS. It's a bit of an evolution, you can call it that, of distroless. It's kind of version 2 of distroless, where we've taken the best parts, stripped out all of those different extra dependencies and things like that, package managers, but tried to do more. We've tried to make it a little bit less. There's, again, no platform tools. There's no way to have a kernel in Wolfi right now. I think it might be on the roadmap one day. It's specifically built for containers. That's it. So all the packages that are in Wolfi are just for containers. It's a rolling release cycle. And this may be a little off-putting to some, but the idea here is when you run Wolfi, when you run any package in Wolfi, it's always patched, it's always up to date, it's always the sort of, if you're familiar with Arch Linux, it's always running the latest version of upstream. Whatever the maintainers have said is the most sort of up-to-date, patched, feature-complete version of the package, that's what's shipped in Wolfi. And so by doing that, by adopting that kind of a posture, you if there's a CVE, there's a patch that comes out. Most of the time, we end up getting patches in before scanners even detect the vulnerability. Because we're just pulling right from upstream, doing. One of the ways that we do that is we use the APK package format. So if you've used Alpine Linux, Alpine uses its package format APK, not to be confused with Android APKs, totally different things. That threw me at first. But the APK package format is really interesting in the way that the package manager, the dependency solver works. If you can build a package and it builds successfully and you can install it, then you know that that package is installed. There's no real indeterminate kind of a state. I think I'll talk about it a little bit more later. But we picked that package format for a reason, because we want to have that kind of reproducibility. We want to have that guarantee. If you say that you've installed a certain package at a certain version, that's what's on disk. Some of the other distributions don't behave that way. There's some nuances to the way their package managers. SBOMs. So SBOMs are first-class citizens of Wolfi. Anytime we build a package, there's an SBOM. The Cyclone DX, SPDX, we include them all. When we build images, you ship the SBOMs with the images as well. They're part of the image manifest in the registry. We publish attestations as well, so they're cryptographically signed. You can go and verify this image was built with this software, with this build system, with this identity token, so on and so forth. So you can verify the whole chain, the whole provenance chain, right down to the commit in GitHub code in our repository. SBOMs, if no one's familiar, if you haven't heard, software bill of materials, again, they came out of that executive order, and this is just like that. The ingredient list for all the different components of your software, so versions and things like that. Wolfi packages are declaratively and reproducibly built. So we rebuild everything. If there's a Go toolchain patch that comes out, every single package that depends on Go gets rebuilt in Wolfi the moment that patch comes out. I think the last one, it took about a day to rebuild everything, but that's how it works. And when you see the files, they're YAML files. There are maybe better or worse formats, but YAML is what we settled on. And again, you can look at those files and you can kind of reason about them. You're going to know what's in your packages by quickly reading over it. It's more of a declarative type of a format where you can see what a final package is going to look like without seeing all the individual steps of how you get there. That's certainly there. But generally speaking, I'll show you an example later and it'll make more sense. And we're targeting x86-64 and ARM64 architectures. You can also build S390, RISC. I think there's a few others, maybe MIPS. But we're not building all those packages. So if you wanted to have one of those packages, you'd be on your own. The toolchain supports doing it. You just pass a target of like S390. And if that package compiles, if you've got the right environment, then you'll get your 390X package. But so far, we're just targeting these two architectures. So I think every package has one of both. Yeah, so why APK? The idea with APK right here, I'll just put it all up on the slides, is it's declarative, it's reproducible. The way the package solver works is if you install a package with APK, it's going to walk the graph of all the dependencies. If there's no problems, your package gets installed, that gets recorded into your APK world file, and you're all set. You know what you've installed is what's on disk, and you can just continue on. And so this is great. If there's ever an error, if there's ever a conflict, if you're familiar with, say, installing a package in Debian, and you get halfway through a post-install script and it fails, it hits a permission denied thing, or there's all sorts of different errors that you can run into. Now you might be in an indeterminate state. You don't know what pieces of that package are installed or are not installed. You might have conflicting versions of a package. Maybe something got halfway through removing an older version of Go or Java or something like that. And so now you're not sure. If there's no error that's thrown in that situation, you might be shipping like a half-built image into production. Whereas with APK, APK says either it works or it doesn't. If it doesn't work, it doesn't roll anything back, it just fails. And so this is really great for CI/CD pipelines because if your build passed, at least at that point, you know that the runtime environment is good. Whether your application is good, that's all on you. That's not us, right? But at least you know that you can ship something reliable into production to be able to run your applications. So that's why we went with the APK package. There's a slide at the end with more if you want to see our staff engineer or principal engineers sort of reasoning about that. They tried a bunch of different approaches. They tried using Debian packages and paring them down, and eventually just landed on, APK is going to work for what we are trying to do. So if you want to follow along, I would suggest get this running now. I don't think too many people have laptops, so I might just sort of power through this and show you, and I'll get to the end. But this is our SDK image. So you don't have to use the SDK image. You can use all of our tools. They're standalone. They're just Go applications. So if you're familiar with the Go ecosystem, you can say Go install APKO, Go install melange, and you can build all these container images without having any container runtime at all. So it's designed to be run anywhere. And I promise, we're at OWASP conference, LastCon here. We're not trying any container escapes with that privilege flag. It's just to be able to run some of the QEMU emulation to build different packages for different architectures. We have to have that extra flag. It pulls down a couple of extra dependencies. So yeah, we can scan some images. Let me do this. Let me just get a terminal. And let's see here. Where am I? It's a little bit small, isn't it? So let's scan the node image. And I'm going to do this right here. Just gripe node. I have the image already, so I'm not going to the registry. If you know gripe lets you scan things like SBOMs. You can pull an image directly from a registry as opposed to your local copy. Supports lots of different options. So this is the node, again, node latest. You could pull this from Docker Hub. And here's our list. This one's been bugging me for a couple of days. It's been there. It hasn't gone away. This is zeblib vulnerability. But I'm scrolling here. These are all, the package format is Debian packages, right? You should be able to apt update, apt upgrade, and get rid of all of these problems, right? But you can't. Look, we've got, say, things like image magic and magic wand for doing image transformations. Lots of different attacks against image processors. This is all built into the node image. I think if we look, I think it's got GCC. So if you wanted to have a compiler and a linker, you've got that in your node image as well. That's great for an attacker. If you want to do living off the land, that's like walking through the forest and coming across a fully stocked mansion with the lights on and a butler at the door inviting you in. Yeah, there's your compiler, GCC. There's our package manager. So if I don't have Nmap, I can just go apt install Nmap, and I can start to do some scans across the network. I can go and, compile hping or whatever tool it is that an attacker wants. Basically, the sky's the limit here, right? That image as well, if we were to say Docker run node, runs as root by default. So you're running your JavaScript code in your node environment. By default, if you haven't done anything in your Docker file, you're running as root. I mean, you've got access to all these tools. So you've done your attacker's work for them by using this image. Let's look at the other image. So just as a point of comparison, I think I've got this one. I don't have it locally. Okay, it's only 46 megabytes. If you look at the Node version I think is a gigabyte. So even there, just for efficiency purposes, it takes a lot longer to download a gigabyte than it does 46 megabytes. I thought I had this pre-cached, sorry. Tell you what, I'll come back to it because I know lunch is happening, so I don't keep people, it's 11:30. But this again, if you were to scan all these different images, again, go on Docker Hub, look at Java, look at Python, Ruby, Postgres, Bazel, all of these things. If you do those scans, this is a year out of date as well because we've targeted 0 CVEs, so those little blue ones for our images, for Wolfi-based images, we've got no CVEs. We're not shipping a vulnerable runtime environment.
You're good for 15 minutes. So
Yeah?
no
Okay,
worries, yeah.
perfect. I want to get to the demo. The demo's the fun part, promise. So a couple of things. Again, Wolfi, the operating system itself, we've got this GitHub repository. The whole thing is just run with GitHub Actions and runners. We built the entire distribution basically around using GitHub. We use apko, melange. When we build our images, we're using Terraform inside of our GitHub runners as well. So the whole thing is right there. I think, let me just escape out of here. We can take a look. This is the repository. I don't actually know how many packages are in because we've truncated. Okay, we're up to almost 2,000 packages right here. Again, I'll show you what they look like in a little bit. So we've got Wolfi. We've got ChainGuard images, which are just our versions of Wolfi packages packaged up into our runtime environment. So if you're curious about that, you can pull, again, it's all right there. You can go look at the repository. I think 200 or 300 images of all the sort of large ecosystem things, especially CNCF packages. If you're doing anything in Kubernetes, there's a Prometheus exporter for basically any kind of thing you could be running, so on and so forth. So ChainGuard images, let's just look at those quickly. This should look pretty familiar from before. Here's our Golang image that we built. Here's our main Hello server. Drop-in replacement. Just pull down the ChainGuard Go image. It's like 100 megabytes. It's got way less packages. It's got 0 CVEs. Basically the same thing. Instead of using the scratch image, we're just using an image we call static. Same thing. It's got your glibc runtime. I don't know where our TLS certificates are. I think I might have tried to save some space on the slide. But it's essentially a one-to-one drop-in replacement. So you can just go do this today. If you're building a Go application, Python application, a lot of times you can just drop your code in with the copy command right here. Do your build, whatever it is, copy from your builder into your final image, and you're all set. Now, if only it were that simple, I wouldn't be here. So there's a lot more to it, but this is a good start. So that's the Docker way. That's the way we've been doing for, I don't know, how long has Docker been around? It's got to be almost 10 years, right? Yeah. So what's the Wolfi way? What's the new sort of paradigm shift that we're trying to sell everybody on? It's using these two tools that we've built called apko or apko, depending on who you ask, and melange. And so we've got a tool for building images and a tool for building packages. So apko works with that APK package format. So it uses APK files, packages, to build OCI compliant images. That's the first part. So at the end of the day, you still get an image you can load into your Docker daemon, and you can run it. Fully reproducible again. Anytime we build an image, we've had customers come to us and say, hey, you say you're rebuilding all your images nightly, but we don't see any change. And that's because it's reproducible. If nothing has changed, when we rebuild it, you get the same commit digest that went into that image however many times you built it. It's always the same, unless you've actually changed the binary contents that have gone into that image. Things like date stamps, eliminate all of that. That doesn't make for a reproducible build. You always get the same image. Anytime you run apko, it'll just rebuild, and it'll either do nothing because nothing has to change, or you get a new image. Again, you get these attestations. So we're using in toto attestations, where we'll publish things like the SBOMs, the image manifest itself. Again, they're all cryptographically signed and attestable to our keys. And you can go and you can look at that whole history of that image, see where it was built, how it was built, everything that's inside of it. With APKO, this is I think the interesting part. This is the declarative part, where there's no run statement. You know, with Docker, it's just that series of steps. You go one by one. There's none of that with APKO. APKO, you say what you want the final image to look like, what are all of the pieces, and APKO goes and it solves that for you. And so it shifts the burden of doing all of that into melange. When you're building your packages is where you do all of your different pipeline steps, which is more, I think, how we've always done things in the past. You run make, you run configure, you run Maven, you run Ant, whatever those tools are, you run those tools when you're building a package, not when you're building an image. And so that's why APKO doesn't do that. There's no run in APKO files. We end up getting small images just because, again, we know the set of things that need to be there for a runtime environment for a given package. You declare what are the runtime dependencies for this image. They're different from the build environment dependencies as well. So, you know, instead of having Scratch images and builder images, when you build a melange package, you say, what are the packages I need for the build environment? And then what are the packages that I need for the runtime environment? And APKO and melange will look after solving those for you. So it ends up being pretty fast as well. It's a Go binary, essentially. But again, it doesn't have the overhead of having to run everything through a Docker daemon and making different layers and things like that. You get a package at the end of it, and you turn that into an OCI image. So here's what an APKO file looks like. Again, YAML. It's not super nested, hopefully fairly legible. I'd say it's no better or worse than a Docker file, right? So first off, we know we're just pulling down. We're going to use Wolfi as our OS. You could use Alpine. You could absolutely build Alpine packages using APKO and melange. So we're saying we're going to use the Wolfi repositories, use Wolfi's key just to be able to verify our packages. And what does this hello server need? It needs to have CA certificates and the hello server package itself. Hello server package itself is going to come from melange. We're going to build that. Here's what makes this, you know, right away. We're seeing we're running as this user. We're not running as root. So we've specified our container by default. If somebody gets in, at least they're going to have to do a little bit of work, maybe burn a 0-day or something on getting root to do some privilege escalation if that's what they're after in their container. And then here's our entry point and our command. So that's what we normally associate with an OCI image, like your Docker entry point or your Docker command. So again, notice there's no order of operations. There's no steps. You're not defining any of that here. You're just saying, this is what I want my image to look like. I want to have this user. Here's some packages. Here's how this image is going to run. Melange itself, the idea here is we can declare different types of pipelines inside melange files. We can have sub-packages, like a package for documentation, a package for any dependency. The list goes on and on. By default, we do those multi-architecture builds. So if you don't pass anything, you're going to get your x86 64, you're going to get your ARM 64. I forget the whole list. Everything's signed, every package is signed, so melange won't even do a build if you don't have a key. You have to generate your own key, and it's up to you how you're going to distribute that or not. But this is what a melange file looks like. So again, YAML. We're just defining our package. We're calling it hello server. Here's the build environment. So notice this is not runtime. This is build environment. And so we want to have our whole library of those 2,000 Wolfi packages available to us. So we need our certificate bundle. We need a shell, just some core utils, things like that. And then Go, the Go compiler. Here's the pipeline. And this pipeline, you know, it could be multi-line YAML. So it could just be a whole bunch of steps. We're doing that same thing. There's our Go build. And we're going to output the binary into the target file system for our package, which is this target destr variable. And that's it. That's going to build our Go application. Instead of doing Go build inside of a Docker file, we're building an APK package. The melange is going to capture all those different files. It's going to have a signature. It's going to be a package that you can install using APK add. It removes all of that work from building images to just, I need to have this package in my image, and it's just going to show up like any other package. So let's do this. We've got a couple of minutes. Anybody who wants this to see how we build images, we can do this. So there's the repository. I've already cloned it. If you've been following along, let's see. We've got a README, and we can just follow these steps. So here, Docker, we've got that. We've cloned the repository. I'm in the Hello Wolfi directory. I've got the SDK as well already. I already even did some scans. I did the gripe scan on Node, and I showed you the ChainGuard version. I think that maybe is done. Did that finish? It might be a different terminal. Anyways, let's just keep going. So let's go look. We've got a Python application right here. Let's build it the Docker way first. Then we'll do it the Wolfi way with a Docker file, and then we'll do it with apko and melange. So first up, what is it? Python web app Docker. And this is just a Flask application. Flask is a little micro framework in Python. It's like, I think it's single threaded. It's what I learned to program with. It's been around for a long time. It's a great little piece of software. So pretty straightforward. All this is doing is just running. Basically, anybody hits the root level URL of your application, they're going to get hello world. That's all this application is doing. We've got some requirements. This is just the way that you package up Python dependencies, where you pin versions. This is, you basically, get your application running, you do pip freeze, you output it to requirements.txt, and it's like your pom.xml or your package.json or your, what's the gem one, the bundle, something like that. It's just a file for the Python ecosystem. And then Docker file. So this is pretty straightforward. This is just pulling the upstream Python 3.12 latest and greatest Python right from Docker Hub. It's got a billion pulls and lots of stars. It's making a work directory called app, so that's where we're going to put our main.py file. We're going to copy in our requirements file. We're going to install our requirements using the built-in Python package manager. It's going to go right into PyPI. So our image has pip, right? It's installed right there. We're going to copy our main.py, make sure it's available on port 8080, and then when we run our container, it's just going to run Python app.py. So hopefully pretty straightforward. So I can do Docker build, and I think I've got this one right here. I'm going to tag it Wolfi Hello Python just to do that. Again, I pre-cached this. This would take a while. I think that image, let me just see how big it is. It's a gigabyte, right? That Python builder image is a gigabyte. So you've got all that stuff if you're using that as your actual runtime image. But there it's all built. So now I can do Docker run. Port, what is it, 8080. And there's my Flask. It's up and running. And there's my hello world. Great. So I've deployed my web application, right? That's my container. Pretty straightforward, common, normal way of doing it. If you've done containers, this should look pretty familiar. So let's move on to the next version. The next version is, we'll go do the Wolfi way, just to show you how you can do a drop-in replacement. And so same thing. We've got our main.py, just showing you it's the same file right here, same requirements, and then same Docker file. The only thing we're really doing right here is using the Wolfi image for Python, the latest dev. So all the images that we have like a runtime image and we have a dev image, because it's really inconvenient to not have a package manager and not to be able to figure out what are the dependencies that I need from the operating system as opposed to pulling everything down with pip or something like that. So all of the images, basically everything we make, has a dev version that includes a shell and a package manager so that you can figure those things out as you're building your package. It's kind of a convenience thing. So same thing, work your application, copy your requirements over, run our pip command, and then when it comes time to build our image, we're going to use the Python image as opposed to the Python dev image. And so that's going to strip out, again, all of those things that you don't need. This is that sort of distroless version. Same thing, workdir, we're going to copy over, literally when we did that pip install inside the builder image, we've got all those files, we need to copy them out of there into our runtime image. So it gets a little bit inconvenient. You have to understand package managers, where they're putting everything. But that's all this step is doing. right? It's copying when I do pip install, it's copying Flask and all those different dependencies that are not managed by your package manager. And then same thing, main.py, port 8080, app, So we can do the same thing. Sorry, I just lost my terminal. Okay, what is it, Wolfi? And so this will be hello Wolfi, we're gonna call this one. Again, so we've got our two different images, it's all cached, and we can say docker run. And this time we'll do hello Wolfi. Same thing, looks the same, it's just a Flask application. There's my hello world, right? You can see my requests. So basically drop-in replacement. You can just use your Docker files, go find whatever the equivalent Wolfi chain guard image is, and you can use that for lots of different languages, so on and so forth. But again, I said we can do better, and we can. So let's go look at the apko melange way. A couple of different files here. Again, this is from me doing demos. I think I actually have the SDK, so I'm going to go do that version right here, just because, again, it's a couple hundred megabytes. It takes a while to download. But this is the same directory. It's just mounted in. I ran what? This is the command that I ran to get this development container right here. So we've got melange. And this is what we need to be able to get our Python file into an APK package. So it should look pretty familiar. Here's our Python app. Here are the architectures we're targeting. We could take one of these out and just do x86 64. If you know you're not building for ARM, why bother building for ARM? It's going to take up space in your archives, so on and so forth. Here's the repositories that we're using. So again, you could do this with Alpine or any other APK-based distribution. Here are build time dependencies. So we need to have, we've decided we need, when you're building Python, you might have to be building some, say, C bindings, things like that. So there's going to be a couple of tools to be able to do that. A shell, Python, pip. This should look sort of familiar. Here's our pip install, right? That same command that we did before in the Docker file, pip install requirements. That copy command, running the copy from the builder into the actual runtime image, that's what we're doing right here. We're making the directory, we're copying all of the files that we just installed with pip into our final target APK package, not into the image, right? This is an APK package that you can do APK install with. We're also making a directory for our application itself, so for our Python code, not for all the dependencies. And we're copying that into the final package as well. And so we can say melange, let's see, melange build. We're going to target just our target host architecture. And here's the signing key. I've already got a key set up, but I could do melange keygen and it'll generate a key for you. And so what's going to happen, it's going to set up a little temp file system. You think of it like a CH root or something like that, where it's just the things for this build. Depending on your platform where you're running melange, there's different ways of doing containerized builds. So you can use things like bubble wrap, Docker. I think there's a couple different ways that melange is set up to do it, depending on where you're building. We can see, it's downloading dependencies, things that we need. Lots of caching, so it makes it pretty quick. If you can put that cache into a volume in your CI/CD pipeline, you can have a pretty much complete set of packages where you don't have to go download them. Again, they're all reproducible, they're all cryptographically verifiable, so the package that you're installing is, your base layout or your glibc, it's always going to be that package. So you don't have to go download that every time. So melange is pretty good about doing that aggressive caching. I'm looking, where's the build step? So here it's using bubble wrap inside my container. Here's my pip install. Sorry, I'll highlight that. So there's my pip install, there's my makedir commands. It's just showing me that output in line. Here's my actual output from pip install. Oops. Showing me all these dependencies. I think this is all intermixed. So it's because things are running in parallel, because builds are declarative, this output is coming after, but sometimes there's other stuff that it gets mixed up. You just have to know what you're looking for. But at the end of it, finally, we get this rote packages, arch, Python, web, app, blah, blah, blah. So let's take a look at that one. And there's our Python web app. Here's our APK index. We can go, tar, we could look at that file. Sorry, not file. And we can see everything inside it. So look, we've shipped our SBOM right inside that package, so we can verify that. It's inside the package itself. Here's all the dependencies, our Python packages that we needed for our application. Somewhere here in this package will be our application code as well in OPT. But that's it. That's the only things in this. So remember how I had build base, I had CA certificates, I had all of those things in the build environment. None of that's included in this package. All that I have is my application code and the dependencies that it requires. So now I've got that. Now I can actually build my image. And so this command right here, apko build, again, target my host architecture, turn on some debug logging. I've got this file called apko.yaml. Let me just show you that file. Should look pretty straightforward. Here are the packages we need. We need Python 3. That's our interpreter. That's our runtime environment. We need our Python web app that we just built. And so apko will go find that local package repository that I just made. It'll find my Python web app application. It'll see there's a key there it's signed. It can verify that signature. It's going to create this user, this group. It's going to run as this unprivileged user, and it sets the entry point to our application. So hopefully pretty straightforward file to reason about. So apko build. And what else? We're going to call the image Wolfi hello apko melange. It's going to output it to a tarball. So that's our OCI image. If you've ever done Docker save or Docker export, that's the same thing. It's just a tarball of all those different layers. And then the key ring. So we want to verify our package. That's why we're passing this in, so that apko knows to trust our Python hello app. So we do that. We, again, grab some runtime dependencies. There's our Python. We've created our user in our group. We've generated our tarball. Here's our image digest. And finally, at the end of it, we have this image.tar file. We can take a look at that file. And there's your regular OCI layers and manifests. You can load this right into Docker. So I can do that. I'll just exit out of here. I've got my Python web app apko. Here's my image.tar file. I can say docker load. It's only 27 megabytes instead of, what was it, 50 or so for the other Python one, using our chain guard Python. And then I can say docker run t port 8080. There's my hello world. And there it is. So it's the exact same thing. At the end of the day, you get the same thing. There's no shell in there. I can't exec in there and run anything, basically. If I was doing the, let's say docker run, let's go look at the Hello Python version. We're going to do that. I'll run this in the background. I can just docker exec in here. And now I can do whatever I want inside my Python running image with that update, right? I'm in a full container here using that upstream Docker Hub image, using the one we just built, this one right here, this Hello Python, not that one, this one. I can't exec into that. Sorry, I've got too many things going on. Also, it takes a lot longer to shut everything down in these big images. Anyways, I think, I don't want to belabor the point. It is lunchtime, basically, so let me just finish off here. If there's anything else you want to know, please come talk to me after. I'm going to be around today and tomorrow. We've got the Wolfi community as well. We have office hours every week. If you want to start contributing, I think we're going to be setting up a Discord or a Slack channel. If you want to know more about where apko melange came from, this is a great Twitter thread. You can go look at it. And then edu.chainguard.dev, where we talk about how does apko work? How does melange work? Do you want to look at images and compare a number of CVEs and things like that, some of the graphs that I showed? It's all there. And that's it. Are there any questions? Happy to take some time. Don't feel like you need to stick around. I'm happy to build a package if somebody wants me to like just pick a package and I'll try to build it. I can do that too.
I was curious why you're using modest IP. I mean, there's no interactive shell, but you are still using.
It's just.
You use it privileged.
It's a force of. No, so I didn't use privileged when I was running. Earlier I did. Yeah. No, earlier I did, but.
So that's my general question.
So Docker run, it's a force of habit for here, just from doing dev stuff, where I do, I want to go into those dev containers. I want to run apt update. I want to run pip or maven. It doesn't matter if you're setting that and there's no interactivity. You can pass those flags.
I'm just curious. The only problem with the shell is so you can build one.
But that's the idea, right? Is
Remove the shell.
that's the idea. Is your debugging should be done before you ever ship this to production. So when it does come time to debug it, because you have that image digest, you know the exact image. You can do things like you can just unpack the image. You've got your package as well, so you can install that same package, that exact same package, go install it into the dev container, and do your debugging there. So, yeah, I think not having those things, that's the point. That's just reducing the surface area. It's difficult. When I first learned containers, we were all just installing OpenSSH and we were SSHing into containers because we thought they were VMs. That's how we all started doing it. Oh yeah. No, come on, be honest. We all did it. We all ran you all say user root and then install SSH in your container. That's how I started it. I was working at Canonical at the time. So,
Anyway, good talk.
thank you.